All right, so yeah, in that last video we were looking at convergence for alternating series. Now we want to talk about distinction that is absolute versus conditional convergence. And again, um, this is for alternating series. So if we look at both of these and we want to know whether or not they converge, we could write out the first couple terms just to help us see. You know, let's say n equals 1 to infinity, n equals 1 to infinity. The first couple terms, we'd have 1 over 1. That would be the first term, minus 1 over 2, plus 1 over 3, minus 1 over 4. And we've already looked at this. We know that, first of all, the limit as n approaches infinity of a sub n, which equals the limit as n approaches infinity of 1 over n. We know that this equals 0, so that's the first criteria for alternating series. So the limit of the nth term approaches 0. And we know that a sub n plus 1, or the n plus 1th term, is less than the nth term. And we see, this is less than this, this is less than this is less than this. And since it meets both of these criteria, we can say that our first one converges, and the second one, well, this is going to be the same difference. So we're going to have 1 over 1 minus 1 over 4 plus 1 over 9 minus 1 over 16. So now it's being squared, and once again, we can, if we want to meet the two criteria, the first one is that the limit as n approaches infinity of 1 over n squared. So this is uh, my nth term. This is going to equal 0. So my nth term approaches 0. And the why do I keep doing that? The n plus 1th term is less than the nth term. So it meets that second piece of criteria. So this also converges. Both of these converge. Both of these alternating series converge to a set value. Now, um, these are called conditional convergences, and it's conditional on the fact that they're alternating. It's conditional on the fact that we've got this negative 1 to the n, or negative 1 to the n plus 1. Uh, and now what we want to see is, will they absolutely converge? And absolutely meaning, will they converge if we take the absolute value and get rid of this alternation? So here we have taking the absolute value. And if we take the absolute value, these become series that we've looked at a bunch. This is just 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus dot, 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 dot. And when we take the absolute value, this really becomes just a p series. This is the integral of 1 over x to the 1. So dx. And p here equals 1. So p is less than or equal to 1. And therefore, since p, not less than or, yeah, less than or equal to 1, since p is less than or equal to 1, this is going to diverge. And we've already looked at that these, that this harmonic series diverges. We've already seen that again and again throughout the last couple of videos. So if we took the absolute value, while before this converged without the absolute value, when we take the absolute value, this diverges. So this one only converges conditionally. It's on the condition that it's alternating between negative and positive. It's not converging absolutely. Well, let's look at the next one. This next one converges without the absolute value, but will it absolutely converge? Well, when we get rid of when we take the absolute value, this becomes the sum of 1 over n squared, and so this is a p series with n equal 2, and since or sorry, with p equal 2. And since 2 is greater than 1, we know that this will converge. And just to, in case we kind of forget the idea of p-series, the idea is that if we integrate from 1 to infinity 1 over n squared, well, this is going to be, this would equal, what would it equal? Negative n to the negative 1 from 1 to infinity, which would equal, kind of using ugly math, negative 1 over infinity minus negative 1 over 1, which is roughly 1. So it's converging to a value. And so because this converges when we take its absolute value, we can say that that has absolute convergence. This one on the right converges absolutely, even when we take away the alternating signs, whereas the one on the left converges only conditionally, conditioned on the condition that it alternates. So clearly, the absolute convergence is much more powerful than the conditional convergence. So this is just a definition here. Looking at it for absolutely convergent series, it's absolutely convergent if the series of absolute values converges. And a conditional convergent series, the conditional convergent series is conditionally converges. It's conditionally convergent if it converges, but the series of the absolute values, when we take the absolute value, diverges. So if an alternating series converges both times, if it converges by itself and converges when you take the absolute value, that's absolute convergence. If an alternating series only converges when you don't take the absolute value, then that's called conditionally convergent. And there's an implication being that if the series absolutely converges, then it also, if it converges when you take the absolute value, then um, then it will converge without the absolute value. So in other words, the absolute convergence is the more powerful statement, as I said before. So now, in the last little bit, we want to look at, kind of wrap this up a little bit. Determine whether each of the following series of constants is convergent or divergent, and then we want to classify any of the series as absolutely or conditionally convergent. So let's take a stab at this. We'll start off with A. Yeah, we'll start off with A. So right away, looking at A, we can see that it doesn't look like it's going to converge. In other words, 2/11 is less than 1/3. These values aren't dropping off. So for it to converge, as we go from one value to the next, the absolute value of those should get less and less and less. That's not the case. But the proof of that for A is we can say that the limit as n approaches infinity of my nth term is the limit as n approaches infinity of 2n squared over n squared plus 10n. And using L'Hopital's rule or just our understanding of rational functions, as n approaches infinity, this value approaches 2, which means our nth term is 2. So we're going to continue to add value. It's not 0. And since it doesn't approach 0, we know that this first one is divergent. Cool. What about the next one? Looking at the next one, first thing that we want to do is look at the idea that it is each of these values is dropping. So 1 over root 2 to 1 over root 3 to 1 over root 4. We're getting less and less and less, and they're alternating and get less and less and less. So we know that a sub n plus 1 is less than a sub n. And similarly, we can say that, and that's one of our criterion. The other one is that our nth term, the limit, as n approaches infinity of my nth term, 1 over root n plus 1, this is going to approach, not approach, this, yeah, this will equal 0. So where our nth term is approaching 0 and our n plus 1th term is less than our nth term. So therefore, we know that this is at least conditionally convergent. And the last thing that we need to check is whether or not it is in fact absolutely convergent. So in order to do that, we need to think about it when we take the absolute value. So thinking about the absolute value, that's, taking the absolute value from 1 to infinity of 1 over root n plus 1, or x plus 1 dx. It might be easier for us to think about it if we write it as the integral of x plus 1 to the negative 1/2 dx from 1 to infinity. And when we write it like that, it's clearly just a power rule or reverse power rule that we're talking about. So we integrate this and we get x plus 1 to the 1/2 with a 2 out in front. And to write this better, 1 to some value a, where we're letting the limit as a approaches infinity. So what does this equal? Well, this equals 2 times a plus 1 to the 1/2, or the square root of, minus 2 times 1 plus 1. And clearly, and that's as a approaches infinity. And clearly, using the integral test, this value is going to diverge, because as a gets huge, this value here is going to get huge. So this diverges when we do the absolute value, when we take the absolute value of it. So using our first two tests, we showed that it conditionally converged, and then using the integral test, we were able to show that it was divergent when we took the absolute value. Let me go back. So because it diverged when we took the absolute value, that shows that this is a conditional convergence. All right, now let's look at the last one. I mean, you guessed it. It's probably going to be an absolute convergence just by the setup of the problem. But let's go ahead and show that. So we've got this alternating series, and we want to show first that the nth term approaches 0. So we say the limit as n approaches infinity of 1 over n to the 4. Well, that clearly equals 0. So that condition's met. We can see also clearly that each subsequent term is getting less and less and less because we're dividing by a bigger number. So a sub n plus 1, our n plus 1th term is less than our nth term. So that meets our second condition. Therefore, we know that it is at least conditionally convergent. And then we want to show, is it absolutely convergent? Well, really, really easy one here because we're looking at the sum of 1 over n to the 4th. So this is a p series. P equals 4. 4 is greater than 1. Because it's greater than 1, that implies, because our p value, which is 4, is greater than 1, this implies convergence. So therefore, it is absolutely convergent. And here ends the video.